So for 18.8, we're talking about complex numbers. The reason that they're called complex numbers is because part of the number is real and part of the number is imaginary. The concepts we're going to look at is the definition of I, the powers of I, the definition of a complex number, and then how to add, subtract, multiply, divide, all these different complex numbers. Okay.
Are we doing 18.7 after?
No, we actually skip 18.7. So, definition of I. So an imaginary number is the result of the square root of a negative number. So the square root of negative numbers gives us I. So I is equal to the square root of negative 1, which implies that I squared is equal to what? What is I squared equal to? Negative 1. Because remember, if we square a square root, they cancel and we are left with whatever's on the inside. This is an important concept here. Okay. And that's all this definition is saying. What I wrote at the top is just a simplified version of that definition. Okay. So looking at some examples, we know that we could write the square root of negative 64 as the square root of negative 1 times the square root of 64. Okay. All I'm doing is taking that negative out of my square root because we just said that the square root of negative 1 is equal to what? I. Okay. And then we know that the square root of 64 is 8. Okay. But just like with variables, we always want to write that number first. So the answer is 8i. 8i. And that's it for imaginary numbers. Just if we have a negative under a radical, it turns into an I. Okay. So looking at the square root of negative 50, we can say that this is the same as the square root of 50 times the square root of what? Negative 1. Is the square root of 50 a perfect square? No, so we're going to have to use the prime factor tree. So we know that 2 goes into 50 25 times. What's the next prime number? 5 goes into 25 5 times. It's the square root, so we circle pairs of 2. So we know that our answer for the square root of 50 is going to be 5 square roots of 2 times, what's the square root of negative 1? I. So where's that I going to go? Is it going to go after the square root of 2 or after the 5? After the 5. So this is 5i square roots of 2. Okay, so we already learned how to simplify square roots. We are just adding the concept of imaginary numbers. Okay. Now looking at number 3, we have an additional negative on the outside, so we just have to keep that in mind. So we could write the square root of -4 as the square root of 4, and I'm going to include that negative in the front because of this negative on the outside, times the square root of -1. We know that the square root of 4 is 2. I'm going to bring that negative with it, so -2. And what's the square root of -1? I. So the answer is -2i. Again, our answer has a negative in it because of the negative that was outside of the problem. Okay. How would I write the square root of -29? How would I write that as 2 square roots? Square root of what? So 29 times the square root of -1. The only reason I'm writing that -1 after is to remind us to put the I after the number. Okay. Can we take the square root of 29? No, it's not a perfect square. Can we do the prime factor tree for 29? Are there any prime numbers that go into 29? So what does that tell us about 29? It's already simplified. It's prime. Meaning our answer is I square roots of 29. If we can't simplify the number, we always just take out that imaginary part. Okay. Looking at number 5, we have the square root of a -100 and the square root of a -25. Are both of those square roots perfect squares? Yes, so what do we get on the numerator for an answer? 10i. Good, because the square root of 100 is 10. We have that negative under the square root, so that tells me I need an I. What about the denominator? 5i. So just like variables, the i's can cancel out. So if we know that the i's can cancel out, we are left with 10 over 5, which reduces to 2. So 2 is our answer. Okay. Any questions so far? Okay. Same with these ones. Looking at number 6, does number 6 have perfect squares? Yes. So for the first radical, how do we simplify the square root of -25? Good, we could write out our separate square roots, but since it's a perfect square, I'm going to go ahead and skip that part because I know that the square root of 25 is 5, and since I have a negative, I'm going to put a I times, what's the square root of -9? 3i. So again, just like a variable, I times I is I squared. So that means we have 5 times 3, which is 15, I times I, which is I squared. But going back to the top for our definition of I, we said I squared is equal to what? -1. Okay, that is just part of our definition. Okay, so that means we have 15 times -1, which is -15. That is our answer. So on an exam, if you leave this as 15I squared, that is not simplified. Okay, you'll get some points for getting to that answer, but you have to remember that I squared is -1. And remember, you'll have your notes and everything for the exam, so nothing that has to be like memorized. Okay. Looking at this next part, can we simplify the square root of 5? No, that's not. So first, it's not a perfect square, and prime is all, never mind, I give you the answer. 5 is also prime. So since 5 is prime, I would write the square root of -5 as I square roots of 5. All I'm doing is taking out that negative and turning it into an I. So I'm doing the same for the next part because they are the same numbers. So since I need to multiply these, we multiply the outsides and then we multiply the insides. So what's I times I? I squared. And what's 5 times 5? 25. Which means my answer here, that I squared turns into what? -1, and the square root of 5, the square root of 25 is 5, so that my answer is -1 times 5, which is -5. Okay. Or again, you could have remembered that square root of 5 times square root of 5 means the square roots cancel out and you're just left with 5. Any questions on that first concept? So learning about I. Okay. Now we're going to talk about the powers of I. So you're not going to see this very often. Honestly, after these notes and the test, you probably won't see it again. This is just telling us about the powers of I. So here's a table that says if we raise I to all these different exponents, these are the answers we're going to get. So for example, I raised to the power of 1 is just I. I raised to the power of 2 is -1. I raised to the power of 3 is -I. And so on and so forth. What's the pattern here? Good. So if it is being raised to a positive even power, so 2, 4, 6, 8, so on, notice how the answer is always a 1 or a -1. Okay. If it's being raised to a positive odd power, it's either going to be I or -I. So we're going to keep that in mind. Actually, I'll write that off to the side. I to odd gives us I or negative I. I to even gives us 1 or negative 1. And we're going to use that idea to make sure we're getting the correct answer when we solve. Okay. So looking at number 8, we have I to the 13th power. So first of all, 13 is odd, so we know our answer is going to either be I or negative I. Okay. So let's go ahead and look at that. So the way we do this is we already know that I squared is equal to negative 1. So we need to separate this in terms of I squareds. So I to the 13th is the same as saying I squared times I squared. So that's 4 i's. I squared, that's 6. 8. Oops. 10. And 12. So that's 12 i's right there. I squared times I squared times I squared. That's that many times to I to the 12th. But we want I to the 13th, so we're going to have an additional I. So pretty much if we add all these exponents together, we should get 13. We know that I squared is negative 1. So we have negative 1 times negative 1. So we're turning all these I squareds into negative 1. Then we're going to count the I squared. So we have 1, 2, 3, 4, 5, 6. So we have 6 negative 1s being multiplied together. That tells us we're going to have a positive 1 or a negative 1. So think of negative times negative times negative times negative. If we have a even amount of negatives, that's going to become a positive. So all of this right here becomes just a positive 1 times I. 1 times I is what? Just I. Remember, I squared is negative 1. So that tells us that I to the 13th is saying that's the same as just I. Again, this is just a concept so you have that knowledge in the back of your mind. This is not something that you will see often or probably ever again after this. Okay. We could also use the chart to our advantage. Okay. So looking at the chart, what's another way that we could write I to the 18th? We could say that I to the 18th is the same as saying what? So remember property of exponents. If we multiply, that means we're adding them together. Good. I to the 9th times I to the 9th. And looking at our chart, what's I to the 9th? I. So I times I gives us I squared, which is negative 1. Which makes sense because we said I to an even number is either 1 or negative 1. So the two ways you could do this. You could write them all out, or we could use our chart. And you're going to have this chart on the test. Okay. What about I to the 107? Using our chart, we would want to use that. Well, we can use any numbers on the chart. Would you guys like to use I to the 10? So we know there's going to be how many of those? 10. I to the 10, 10 times, right? Would just be 10 I to the 10. And that puts us all the way to 100, right? What would we multiply this by? I to the 7th. So we know I to the 10th is what? Sorry, not 10, not 10. This. It would be to the 10th power, yeah. So we know I to the 10th is -1, -1 to the 10th power. And we know that I to the 7th is, look at our chart, -I. -1 to the power of 10 is going to give us a +1 or a -1? +1. So this gives us 1 times -I, which gives us -I. Okay. How could we write I to the 32 using the chart? And there's so many different ways we can do this, so it's whichever way you think of first. How could we do I to the 32? I to the 8th and I to the 4th.
No, kind of like we did the I to the 10 to the 10.
8th to the 4th. But remember, we are adding the exponents when we multiply. So I to the 8th and I to the 4th would just be I to the 12th.
No, what I'm saying is kind of like in number 10, how you did I to the 10 to
Oh.
the 10th. I was saying I 8 to the 4th. So you would be multiplying the 8 and the 4th.
Good. Yes, that would work. I to the 8th raised to the 4th power, because a power to a power means we multiply. That's perfect. So we know I to the 8th is what on our chart? 1. And if we raise 1 to the 4th power, we get 1. Because remember, anything to a power means we multiply. So 1 to the 4th is 1 times 1 times 1 times 1. Those 4 times. Okay. And that ends that concept. So for here, you'll have the chart with you. Use the chart to your advantage. Okay. So now that we talked about the imaginary number, we are going to talk about complex numbers. Okay. Not all of this is important to write down, so definition of a complex number. A complex number is the number in form A plus BI, where A is real and BI is imaginary. So this is real, this is imaginary. Okay. Honestly, that is the most important thing. from this definition. Okay. So again, if you want to come back later and you want to write all this down so you have it for the notes, you're more than welcome to. What I put there for the definition of complex number is as much information as you need. You just have to remember that a complex number is an imaginary number attached to a real number. So looking at number 12, all we're doing is identifying which part is real and what part is imaginary. So which part's real? We have -8 plus 2i. Which part's real? -8. Which part's imaginary? 2i. Okay. For number 13, we have 3 halves. So first of all, if we just have 3 halves, is this a complex number? No, it's not complex, because the only part of the number we have is what? 3 halves is real. Okay? Think of real as something you can count to. You can count to 3 halves, you can count to -8, but you can't count to 2i. For this one, is number 14, -1.75i, is that complex? No, because it's missing what? It's missing real, because this is imaginary.
So when you say connected to, like a real number connected to an imaginary, you mean like with plus or minus?
Yes. And that's all for that concept. Learning the difference between real and imaginary. It's only imaginary if you have an I. Okay. Now let's look at some examples of how to add, subtract, and multiply complex numbers. So in all these examples, we are going to have 2 complex numbers. When we are adding or subtracting complex numbers, you only add or subtract the real numbers with the real numbers and the imaginary numbers with the imaginary numbers. So first, before we add, tell me which numbers in these 2 complex numbers are real. 1 and -3. Which parts of these numbers are imaginary? Okay, which means we are only adding those corresponding values. So that means our answer is going to be 1 plus -3, which is -2, and -5i plus 7i, which is positive 2i. That's our answer. We only are adding or subtracting the corresponding real and imaginary parts. So think of them as that they are not like terms. Okay? Imagine that I like a variable. You wouldn't combine an x with a constant number. Okay. On number 16, which part is real? -1/4 and 1/2. So we're going to subtract -1/4 minus 1/2. And I'm going to write this down here because we are dealing with fractions. Okay. And then what parts are imaginary? Good. So I'm going to write that down here because, again, we're dealing with fractions. Okay. So for the first part, negative 1/4 minus 1/2, we need a common denominator, and what would that be? 4. So what are we going to do to the second fraction? By 2. Okay, which means we have negative 1/4 minus 2/4, which gives us what? So they're both negative, so we add them. So negative 3/4. That is our real part. For here, we have a negative and a minus sign. That's going to turn into what? Positive. And then we have the denominators 4 and 10. So what's going to be the common denominator? 20. So that means we would multiply the first fraction by 5 and the second fraction by 2. So that means we get 15/20i plus 2/20i, which gives us 17/20i. So that is the complex part. So that means our answer is negative 3/4 plus 17/20i. Again, we just add the real parts, then we add the imaginary parts. Any questions so far? Okay. Okay, number 17. We are first just going to change these radicals into an imaginary number. So without looking at how we can simplify the numbers under the radical, we know that the square root of negative 8 equals what? Without simplifying the numbers, we're just taking out those i's. I square root of 8 plus, good, I square root of 18. Okay. The only way that we could add these together is if our square roots are what? They have to be the same. They have to be equal. So we would try to do the factor tree off of both to see if we simplify these, if we could get radicals that are the same. So off of 8, we know 2 goes into 8 4 times, and we end with 2 2's. And off of 18, we know 2 goes into 18 9 times, and we end with 3 and 3. Since we're taking the square root, we are circling pairs of 2, which means for I square roots of 8, this simplifies to what? Just that first term. Yes, 2i square roots of 2. Okay. What about that second term? That's going to simplify to 3i square roots of 2. Now do our square roots match? So if they match, we now add the outside terms. So what's 2i plus 3i? 5i square roots of 2. That's our answer. When we're adding or subtracting, we cannot do that unless our square roots are the same. Okay. But again, this number is not complex. It's completely what? Imaginary. Okay. Now we're looking at multiplying. So if we pretend those i's are variables, we would use what method to simplify this? The FOIL method. So we're going to do the same thing. Okay. So we have 10 times 2, which is 20. 10 times 3i, which is 30i. Negative 5i times 2, negative 10i. And negative 5i times 3i. Good, treat it like a variable, I squared. Now we are going to combine like terms. So 30i minus 10i is 20i. So I have 20 plus 20i minus 15i squared. We know that I squared is what? Negative 1. So technically I have 20 plus 15 plus 20i, which simplifies to what? 35 plus 20i. That's my answer. I cannot combine those because 35 is real and 20 is imaginary.
Because we're just simplifying, would we want to take out a GCF for any reason with that?
The only reason I would take out a GCF is if you had a denominator that could cancel with it.
Gotcha.
Okay. But if you do take out a GCF, I'm not going to mark it wrong. There's just no reason to. Okay. Let's look at 19. So again, we have two complex numbers being multiplied, so we're going to use what method? FOIL. So we have 1.2 times 1.2, which is 1.44. 1.2 times negative 0.5i, which is 0.6, negative 0.6i. Then we have 0.5i times 1.2, which is positive 0.6i. And we have 0.5i times negative 0.5i, which is negative 0.25i what? Squared. What's going to happen to my two middle terms? Cancel, so I'm left with 1.44 minus 0.25, and what is I squared? Good, times that negative 1. So I have 1.44 plus 0.25, which gives me the answer of 1.69. Is this complex? Is it real or imaginary? Real. Okay, any questions on this concept? So on this one, we were adding, subtracting, and multiplying complex numbers. So very similar to when we were adding, subtracting, and multiplying expressions with variables. Okay. Last concept here is how to divide and simplify complex numbers. So the way we do this is going to look similar to when we are multiplying by a conjugate. So in order to get rid of the i's out of the denominator, we're going to multiply by the conjugate. So for example, on number 20, what would we multiply the top and bottom by? 5 minus 2i. So just changing the sign. And when we do that, that means we're going to do what to the numerator and the denominator? FOIL. So that's what we're going to do. So foiling the top, we have 4 times 5, which is 20. 4 times negative 2i, which is negative 8i. So we did this, and now we did this. Negative 3i times 5 gives us negative 15i. And negative 3i times negative 2i gives us, perfect. Now we're going to do the same on the bottom. So 5 times 5, 25. 5 times negative 2i, negative 10i. 2i times 5, 10i. And then 2i times negative 2i, negative 4i squared. Okay, now we're going to simplify. Okay, so simplifying just the numerator, what is negative 8i minus 15i? Negative 23i. And what is I squared? Negative 1. So that means I have 20 minus 6, which is 14. So that's me simplifying the top. Now looking at the bottom, anything that cancels? Good. And then we know that I squared is negative 1. So that means I have 25 plus 4. 25 plus 4, because this turns to positive 4. 29. So that means I have 14 minus 23i over 29. I always want to write this as real part, imaginary part. So instead of having the whole thing over 29, I can do what to that divide by 29? Good, give it to both. So I have 14 over 29, that's my real part, minus 23 over 29i, that's my complex part, or my imaginary. So I have real and imaginary. If you leave it like this, I'm not going to take off points. This is just to show you that we have our real and imaginary part.
How do we put plus 1 there on the bottom? You cancel the I squared?
Because I squared turns into negative 1,
Yes.
and that was a negative 4 and a negative 1. That turns to a positive 4. Let me write that there. So, plus 4. So that's why we did 25 plus 4. Okay, last one for these notes, number 21. Do we have any i's on the denominator?
No.
So do we need to use the conjugate? No, we don't have to use the conjugate because there's no i's on the bottom. But we do need to simplify. So since we have that square root of 18, what we're going to do is we're going to take 18 off to the side and do the what? Prime factor tree. So I get 2 and 9. Oops. And then 3 and 3. Since it's the square root, I'm circling pairs of, good, so pairs of 2, which is those 3's. And then that means that the square root of 18 is now what? 3 square roots of 2. So I'm going to plug that in for that square root of 18. So I have 6 plus 3i square roots of 2 over 9. All I did was put that 3 square roots of 2 in for my square roots of 18. Can I take a GCF out of the top?
Yes.
Yes, what number? 3. So remember, we're just looking at this part right here. That's 6 plus 3i. So we can take out a 3, and I'd be left with 2 plus what? I square roots of 2 all over 9. Since I took out that GCF of a 3, can I cancel anything? 3 and 9, which would result in what on the bottom? 3. So I would have 2 plus I square roots of 2 all divided by 3. But I want to show the real part versus the imaginary part. So I'm going to give the 3 to both. So 2 divided by 3 plus I square roots of 2 divided by 3. Here I clearly see the real, which is 2/3, and the imaginary, which is square roots of 2 over 3i.